Hello, my name is Craig Chelednik. I am a distance student, also an engineer for Westinghouse in radiation analysis, nuclear operations. My project was I modeled the control rod worth measurements using EMCH. I modeled this in the same way that we actually test control rod worths at sites for reload startups and initial startups. That's one of the things that I do at Westinghouse. When a plant refuels or during any time they move any fuel, they have to verify a few things about their core to ensure that before they get to 100% power, their core was loaded correctly. One of the things that they have to measure is the control rod worth. So I attempted to use OpenMC to measure the worths in as practical of the way as possible. So the background and what I was trying to model, what it's called is low power physics testing. It's testing that's done below 5% power, and as I said, it verifies that the core has been loaded correctly and it's going to operate as expected by design. This is done after any refueling or prior to an initial core startup. There's a series of tests, and what they generally verify is the shutdown margin, which is the control rod worths, the power distribution, and reactivity control. The general steps include: first, safely achieving criticality. A few plants do it different ways. You can either pull all the control rods out and then dilute the boron to criticality, or you can dilute first and then pull the control rods out and go critical on the control rods. The next step, or one of the steps after that, is to measure the critical boron concentration, and that's now your critical, how much boron is in your water or coolant to make your reactor critical. Then you would measure your control rod worth. This verifies the shutdown margin. There's a whole lot of ways to do this. Right now with Westinghouse, we use dynamic control rod worth measurements, which are a lot of complicated equations and assumptions and different factors. That's not what I'm modeling. Basically, the most equivalent to my model would be a bank dilution, where you have all of your control rods out of the core, and then you slowly step in whatever bank you want to measure while diluting the boron out. And then when you get that bank the whole way in and you just are still at just critical, you can measure how much water you diluted into the core, and then that amount of water is equal to the worth of that rod, and you can convert that amount of water to a reactivity value. That's generally the closest that my model was modeling. And then also there's a few other tests, such as measuring isothermal temperature coefficient, which is then used to calculate the MTC. In my project, all I was doing was finding the critical boron concentration and measuring the control rod worth. Now, when we actually do this at a site, we insert the D control bank delta, in about 10 to 20 steps, which think I have here. Which is about 12 inches. And we are critical with that bank in just a little bit so that we have a little bit of room to add or take out reactivity. It's just so that we're able to play with reactivity a little bit. So I tried to model that, and so what I did, well, wait, I didn't. So the plan is to model the reactor with control bank delta in 18 steps, and then do a K-effective search to find the boron concentration that makes the reactor critical at that condition. After that, set that as my boron concentration for all of the models then, and then do control rod worth measurements at that boron worth. So next is the model that I used. I used the generic Westinghouse 4-loop PWR 17x17 fuel assembly. The model that I found, or what I used to model off of, was an initial startup, cycle 1. There's 3 enrichments there. You can see 2.1, 2.6, and 3.1 weight percent. Also in this model, there's 4 control banks and 4 shutdown banks. Control banks are banks that can generally be inserted during operation, especially control bank delta, which is moved in and out occasionally in operation to control power. Shutdown banks are not inserted during operation. They're just there to be able to safely shut down the reactor in the event that they need to shut down fast. So as you can see here, this is where in the reactor these different banks are located. So I modeled just 1/8 of the core because there is symmetry about every eighth. So I was able to get away with just modeling 1/8 the core, and this greatly decreases the computing time needed. So here's a picture of my actual core from OpenMC. Here's the whole 1/8 core. This is for my all rods out condition. And then here is over to here. This square is zoomed in right here. These are the different enrichments. Red is one of them, purple is another one, and green's another one. And this zoomed in is equal to the enrichment map right here. So I think this was 2.1 is red, and so on. They line up there, and here's the. So here are the where control rods would go. When the control rods are not inserted, those locations have water going through them or coolant. So you see the blue coolant, and you can see the cladding right here, and then coolant around all of the fuel rods. So here's a fuel assembly, here's a fuel assembly, so on. Get the picture. As I said, I inserted control bank delta 210 steps, which is approximately 12 inches, and I used the K-effective search to find the boron concentration in the coolant that would result in a just critical condition. Once I did that, I found that the result was 2,295 ppm, and then I went and I plugged that into these conditions in these other models that I made. So then I made a model where it's all rods out, and then just control bank alpha, bravos, so on, in at 2295 ppm. And then I ran each of these models in OpenMC to find the combined K effective in each one of these cases, so that I could calculate the control rod worth. The equation for control rod worth is the change in reactivity is equal to basically delta K over K of each case. So all rods out condition, K effective minus 1, which is criticality, over K effective at all rods out. And then to get the delta is K effective of whatever bank in minus criticality over whatever bank in. This results in units of delta K over K, which is not generally used and reported. And that is converted to a unit called percent millirow, which is also known as PCM, and delta K over K to millirow you just multiply by 1 times 10 to the 5th, which is 100 times 1,000, percent 100, milli 1,000. So convert that to PCM. So here's the results of just the control bank delta worth. Although the K effective search came up with 2295 ppm, when I actually plugged that back into the control bank delta inserted to 210 steps, it didn't come up with exactly 1. I'm thinking it's probably because I didn't use enough iterations or enough particles. I'm not sure, but I'm going to look into it. But the rest of the results were as expected. Once I ran the all rods out, the K effective for all rods out is greater than control bank delta at 210. So that was good. That was as expected. And then control bank delta the whole way in is less than both 210 and all rods out, which is good and as expected. So then I calculated the rod worth of control bank delta with the equation on the previous slide here, and I get 0.018999 delta K over K, which is equal to approximately 1900 PCM. In reload startups, generally any one bank is worth anywhere from 200 to 1400 PCM. That's generally what we see. 1900 is high, but 200 to 1400 is for reload startups. Initial startups have all fresh fuel, so you would think that they would be a lot more reactive, which would mean that the worth of each bank would be greater. So that's what I have attributed this higher than normal rod worth to. I have ran the rest of the cases. However, for the brevity of this presentation, I haven't included those results. If anyone would like to see the results, which will be in my report, you feel free to contact me or email me with any questions. I'll be free and willing to answer any of them. Thank you. Have a good day.